Okay, this is where we stopped off in part one. Now we're going to talk about bonds. We talked about elements, a little bit about what makes up an element, protons, neutrons, electrons. You should have that in your head fairly well. And we talked a little bit about isotopes. So now we're going to move to chemical bonds, how these elements come together, how they stick together and make larger and larger molecules. So when we're looking at the protons, neutrons, electrons, only the electrons are involved in the chemical activity. The chemical activity is a keyword. Electrons occur in energy levels called electron shells, and we'll draw that up here in a second. And when we look at the electron shell distribution, we can look at the periodic chart and kind of see what's going on. And this is, I'm going to give, well, there's a periodic chart. We'll just go straight to that. So what we're seeing here is rows and columns. And everything in this column is going to have it's going to have the same exact electron shell property, in that, if you notice, it has one lone electron in its outermost shell. Okay? And when we move over here to this column, it is always going to have two. Well, it's always going to have a complete outer electron shell. Sorry. So here we go, 2, 4, 6, and 8. And again, outermost shell completely full, 2, 4, 6, and 8. So this column on the left will always be missing one, and this column on the far right will always have a complete one. And then you have the directionality of the column. So fluoride will have almost a complete shell, 2, 4, 6, and then 7. And then everything down here will have those same properties. Oxygen, 2, 4, and then 6. And then when we look at sulfur, 2, 4, and then 6, everything in that column will have that same property. And that's one of the things that makes the periodic chart very useful. And so we'll see, we'll look at that pattern a little more and what it has to do with bonding. So an atom can have 1, 2, or 3 electron shells, and the number of electrons in the outermost shell determines the chemical properties, the outermost. Okay, is it full? If it's full, it's not going to do much of anything. And in fact, when we get back here, we look at all the full shells here on the far right, they are all inert. They don't really react with anything. Okay, so if you go and get those fancy windows that help keep heat out, they're 2 pane, and they fill in between the panes of glass with argon gas, because argon is inert. It doesn't really react. Okay, so its outermost shell determines the chemical property. If it's missing electrons, it's going to react, and depending on how many electrons will depend on how it reacts. And that's the basis of those chemical reactions. But what they try to do, and I talk about atoms as if they were a person, just to make things a little easier to understand. But what these atoms are trying to do is complete their outer shell. So we have carbon. Let's draw a little carbon here. And in its first shell, it has 1 and 2. And then its next shell has 1, 2, 3, and 4. And so it's missing 4. And so what it wants is 4 more. And so what you can think of about carbon is carbon tries to have 4 friends. And in fact, when we look at methane, you have a carbon atom, and it wants 4 friends. 1, 2, 3, 4. And so you bring a hydrogen atom that only has 1 friend, and they bond. And so we end up with hydrogen atoms. And so now the hydrogen has, essentially they share those, so each hydrogen now has 2, which in the first shell is a complete shell. And the carbon now has 8, essentially. And so they've grabbed on, and you can still, there's a lot of energy in methane, but it's much, that chemical reaction has already taken place, and so you're going to have the bonding that goes on, and those bonds are going to be more difficult to break, which kind of helps create that energy. So the interactions you help keep those different atoms close together, and so we call that a chemical bond. And the strongest is covalent, cohabitation. Think of that. So they're habitating together. They are together. Okay, that together type of bond. And so the atoms are sharing 1 or more outer electrons. And so that sharing, because the electrons move from one atom to the other, and back, forth, and back and forth, that creates a very, very strong bond. 2 or more atoms, when they're held together by covalent bond, they form a molecule. Okay. And so in this case, the covalent bond, it connects 2 hydrogen atoms in a molecule of the gas H2. And so if we looked at the periodic chart, we look at our hydrogen, and it would only have 1, one electron in its outer shell. And in the first shell, it wants to have 2. So if you have another hydrogen here, with 1 electron in its outer shell, if these 2 share their electrons, then they're going to create a strong bond. So this electron will move around over here, figure 8 configuration back and forth, and this one here will do the same thing, back and forth. And so that's what creates, and so that's where you get the H2, and it creates a strong bond. And so there's a couple different ways to show bonds. And so the electron distribution, that's here, this column here. So oxygen is sharing, water is sharing, methane, here's the methane we drew. Or you can do kind of the stick figure. It's a technical term is the structural formula, but you have your stick figure here. And so because this is a double bond here, you see 2 there. Because this is bent, you bend the stick figures, and methane right here. And then you have space filling models. And so you can see, you get the idea that electrons are moving in and out. And same thing here. Okay, in this case, the electrons are being shared here, and then here. So those are the different ways to demonstrate it. So the attraction, the electron share, is called electronegativity. And when we look at the periodic chart, it looks something like this. Okay? And as we go from the bottom left to fluoride, there's fluoride right here, it increases the electronegativity. Okay? So fluoride is very, very electronegative. It has a strong attraction, a strong pull. And when it has high electronegativity, it's going to pull more atoms and going to pull a little harder. In molecules where there's only one element, the pull is equal because each atom has the same electronegativity. And so the bonds that are formed are called non-polar covalent. So it's still a covalent bond, it's just non-polar. There isn't a stronger charge on one to the other. So water is different. So water, you have your oxygen and then your hydrogen. Okay, those are, oh, and my pen just went nuts. Okay, and so you're going to have different pull between the oxygen and the hydrogen. And in this case, it's going to create polarity. So the result is a polar covalent bond. A stronger pull on one, the other. And so water is a polar molecule. And that's really important to properties of water. So on this end here, because hydrogen is kind of losing an electron, it becomes a little bit more positive, and just slightly. And so there's a little bit more positive charge on this end, and a little bit more negative charge on that end. And so that's what helps water pull things apart. So it's a polar covalent bond between those oxygens and those hydrogens. So here's kind of a concept check for you to step back and think for a second. The reactive properties or chemical behavior of an atom mostly depend on the number of what? And we discussed that. Take a second and you can watch right here. What is going on here? What is this particular piece? What are the parts in here? And this is showing an arrow moving. Remember this part here and then this part here. Okay, they're going to have different numbers in there, but this electron is moving over here, and then you see the result here and here. So what just happened there, and that should help you answer this question. And in fact, it's the electrons in the outermost shell. And so an ion, okay? So an ion is an atom or molecule with an electrical charge. It has some sort of charge because it has either lost an electron or gained an electron. So pay attention to the wording here, because when you're taking a test, the wording, how it's worded, will be very important. When an electron is lost, you get a positive charge. When an electron is gained, you get a negative charge. Remember, electrons are negative. If you bring more negative in, it's going to be a more negative charge. If you take negative out, there will be a positive charge. So when you have two ions with opposite charges, you get an ionic bond. Salt, meaning a metal and an organic compound, sodium and chloride, is a synonym for an ionic compound, because one loses an electron, the other gains an electron. And there's your graphic. The sodium loses an electron, the chlorine gains an electron. And this is, remember our periodic table, right? So, and these guys right here in this column had full octets, or a full number of electrons in the outermost shell. These guys right here only had one, where sodium is right here. And chlorine, remember, where these guys had 7 and they just needed one more, well, chlorine is right here. So these guys on the far left side, they are the givers, and these guys on the right side are the takers. So sodium gives, chlorine takes. And then because you now have a slightly positive charge and a slightly negative charge, they clump together and make salt. Oh, and my pins and the computer is giving me fits. Give me 1 second to see if I can. There we go. So there's your salt. And if you notice, it's kind of a brick of sodium and chloride, a positive and negative charge. But that positive and negative charge also helps it dissolve because water is polar. And we'll get to water here in part 3. So large molecules get their three-dimensional shape by weak bonds. And hydrogen, as a part of a polar covalent bond, has a partially positive charge. And then you have these molecules, or these blocks, that have charged regions, and they're electrically attracted to, think of your magnets, positive and negative. And so they're attracted to opposite, and they're not attracted to the same. And so because you have these, because of the positively charged regions in the hydrogen atom, the bond is always called a hydrogen bond. So that's another type of bond that you have to know about. The different types of covalent bonds, the ionic bonds, hydrogen bonds, and be able to distinguish the difference. So if we look, right, we have covalent bonds going on between the hydrogen and oxygen here, but between the two water molecules, it's a hydrogen bond. So each one of these between the water molecules is, oh, there goes my pen again, is a hydrogen bond. And let's see, there we go. But you have a polar covalent bond between the oxygen and the hydrogen. So here's a question that you should think about. So if you don't get iodine in your diet, it can lead to a goiter. I think I said iron before. I apologize for that. I was thinking iron and iron deficiencies. But and they put iodine in the salt, and I think I said iron in the salt, and that's not right. It's iodine. If you get too little iodine, you get a goiter. And goiter is not common in developing countries because we put iodine in our salt. So here's a question. Do you think that adding trace elements to food items is a good public policy? Some may say yes because it helps prevent these. Others may say no because do we want the government telling us what to eat and putting things in our food? Shouldn't we be able to choose? That kind of thing. So where do you stand on that? Do you strongly disagree? Do you strongly agree? Why? And so chew on those questions for a bit. Remember that the structure of the atom and the molecules determines the way they behave. So atoms are going to combine to form molecules, and hydrogen and oxygen will react to form water. So you have two hydrogen, dihydrogen monoxide. Okay, makes, and that's what this is. Dihydrogen monoxide. H2O, sometimes you hear it as that. That's what it means is water. And so that formation, when you make water from hydrogen and oxygen, is a chemical reaction. And in fact, there's a lot of energy in that. And so if you look at the space shuttle before, when they used to launch it, they'd launch the space shuttle into space and there'd be this big white cloud, and a lot of people thought that was smoke from some sort of gasoline being burned, but it turns out gasoline doesn't have enough energy to launch the space shuttle. What they're doing is they're forming water, and they're creating that reaction. You have two tubes of hydrogen and one of oxygen, and they start this reaction, and that reaction propels the space shuttle up. Remember, and this is really important because for some reason it's difficult. It's a very simple concept, but some people struggle with it. So chemical reactions do not create or destroy matter. You cannot create or destroy matter. It simply changes forms. It simply rearranges. Okay. And so when we look at the reactants, H2 and O2, when they're converted to water, water is the product. Okay. So reactants, products in the chemical reaction. Photosynthesis is a chemical reaction that's essential to life on Earth. So if we didn't have photosynthesis, we would not be here, because it takes sunlight and converts it into a chemical energy that we can then use for our metabolism. And so that is part 2. There's going to be some questions involved. Make sure you answer those questions, and watch part 3. And give me a second.